Okay. All right, we'll just wait a couple of minutes while people start to roll in.
Hold on, I'll be back in 1 second, Alan.
Yeah, good morning, everybody. Good afternoon, good evening, and thank you for attending Wednesday's EMinar. Today, it gives me a great pleasure to have Jeffrey Love speaking on mapping a magnetic substorm. And this is something that we all, those of us in MT really need to remember more and more, is that often our source fields are not uniform, they're non-uniform. So before I introduce Jeffrey, let me just remind you to go onto the EMinar page on MTNet, and there you'll see all the upcoming EMinars. And in fact, there's another page where you can view all last year's one. And on the EMinar page, you'll see videos of previous EMinars and the presentations and registrations for upcoming links. So you are on a webinar, a Zoom webinar. So what functionality you have, you can send a message to the panelists, you can raise your hand if you want to speak at the end, and you can send a Q&A. I can send a question, and the presenter might choose to answer it on the fly or save everything till the end of the webinar. So please put all your questions in the Q&A and not in the chat. So yeah, back to today's speaker, Jeffrey Love, mapping a magnetic superstorm. And this is absolutely brilliant. As I've said, I work in Canada, so I often do have to worry about source effects, but I think a lot of us tend to forget that our sources are not uniform, and we make that approximation, but how valid is that approximation? And Jeffrey will walk us through mapping a major superstorm today. So Jeffrey is a research geophysicist in geomagnetism program at USGS and studied many aspects of geomagnetism. And these days he works on these three main issues: geomagnetic monitoring of data and MT survey data to evaluate geoelectrical hazards, statistical analysis of rare occurrences of intense magnetic storms, and then analysis of historical records of past space weather events and their impact. So we'll probably be hearing all of these during this talk. So Jeffrey, please, I invite you.
Thank you, Alan. Thank you very much. Let's see, I'm going to share my screen again. Okay, can you see me?
Yep, you're good.
Okay, great. Folks, thank you very much for tuning in, and happy to talk to you about some ongoing research at the USGS. Alan was talking about source effects, and I'm going to talk about sources and their effects on the power grid. There is a lot of work that remains to be done. This is just really scratching at the surface of some very complicated subjects. I'm actually not going to talk about the deviation from the plane wave approximation. Alan, I hope that's okay. But I'm going to talk about what we can do with what we have. There's a lot of approximations involved, and we're going to compare some of the analyses we can do with magnetic observatories and magnetotelluric impedance tensors to see about the predictions we can make with that regarding electric fields, and then compare that with actual impact data just to see if we're on the right track. The analysis is, I think, fairly robust, even though there's actually a lot of problems with the magnetometer data for this storm. That's not really a problem for the MT tensors. So folks, I want to acknowledge my collaborators without whom I could have done very little. Greg Lucas is at the University of Colorado, Josh Rigler at the USGS, Ben Murphy at the USGS, Anna Kelbert Paul Bedrosian, all at the USGS. Some of these names are very familiar to you. I've learned a lot from them. And this is a analysis. Everybody has played a role, a different role, to bring this forward. All right, so this picture shows the Northeast United States, and kind of looming over the horizon there is some aurora borealis. This megalopolis is New York City, Philadelphia, and up here we have Boston, slightly obscured by the clouds, and right here is Montreal. It really kind of puts it all in perspective. And in some respects, it kind of reminds you that the Earth is a little bit small. And so we're interested in this part of the world. We're interested in, the focus here will be on the contiguous United States, CONUS, and the impacts that this storm had on CONUS power grid systems. So let's see here, I can progress forward. So just to bring everybody onto the same page, just to review very briefly what magnetic storms are and where they come from. They originate with concentrations of magnetic energy at the sun. Sunspots are essentially concentrations of magnetic field. And when they abruptly rearrange themselves, they can quickly eject electrically conducting plasma, which, if it's directed towards the Earth, can cause a magnetic storm. It takes a couple of days for that plasma to traverse the Earth-Sun distance. But when it arrives, it compresses the Earth's magnetic field on the day side, extends it on the night side, and causes instabilities and activity in the magnetic field that end up redirecting currents, electric currents, from the magnetosphere into and out of the ionosphere. And some of that causes aurora borealis, which many of you are familiar with. It's a very beautiful phenomenon. It's ironic that during that beautiful manifestation of geophysics, we also have geoelectric hazards, which can potentially threaten and with some frequency interfere with the operation of electric power grid systems. All right, so I'm going to focus on the March 1989 magnetic superstorm. It's one of the most intense storms ever recorded, not the most, but it is certainly the most impactful storm that the Earth has ever experienced. If you're interested in magnetic indices, it had a very large negative DST value. DST goes negative when there's a magnetic storm, and we're interested in the depth of that DST value to characterize the intensity of storms. The storm brought aurora and geomagnetic disturbance to mid-latitudes because the auroral oval opened up actually and started to cover mid-latitudes, including CONUS, the contiguous United States. Storms of similar intensity occur about every 4 solar cycles, and we know that from statistical analysis. So it's interesting and important to prepare for such storms, because we expect that things that have happened in the past will happen again in the future. And so we can expect such a storm to occur, possibly again within our lifetimes. Again, one of the most impactful storms ever recorded, interfered with radio communication, navigational systems, geophysical surveys, and disrupted and damaged satellites. But the storm is best known for causing an electricity blackout in Quebec. And also, it's important to understand that it interfered with electricity systems in the United States, including damaging a high voltage transformer in Salem, New Jersey. And this is actually a picture of some of the effects of this storm. That's a high voltage transformer. This fellow is standing in front of it. And here we have the interior of that transformer after the magnetic storm. It caused this transformer to overheat due to geomagnetically induced currents, and actually damage that transformer. So that's a kind of a visual manifestation of the effects that a magnetic storm can have. Now, the analysis of historical storms informs projects for mitigating their deleterious impacts. And that's an important priority within the US government. I work for the US government, so I do what I'm told. We're working on this with pleasure, actually, to better understand the impacts that storms could have in the future. And some anticipate that if another storm, say as intense as May 1921 or September 1859, which were actually quite a bit more intense than the 1989 storm, if such a superstorm like 21 or 59 were to occur again, it could have significant economic consequence. All right, so I spent some time recently compiling what the power grid industry calls anomalies. These are reports of problems in power grid systems. And I've done that for several storms, including the 1989 storm. All of these reported anomalies were in publications. A lot for the 1989 storm were in a publication put out by the North American Electric Reliability Corporation, but there are other anomalies too, and I just added those to the data set. Looked up the locations of the identified substation, found their latitude and longitude, and I can put them on a map. I have 183 different anomalies, and there on the right, I'm showing the map of where these anomalies occurred during the March 1989 storm. These anomalies include those that were associated with the Quebec blackouts, and you see there's a certain number of anomalies in Quebec. But you'll also see there's a lot of anomalies in the Northeast United States and some in the northern Midwest of the United States. That's interesting, I think. And I just want to emphasize that this list of anomalies is pretty qualitative. I haven't tried to discriminate and find, which anomaly was more significant than another anomaly, because honestly, it's pretty difficult to do that. I'm not an expert in power grid systems. I just assumed that if the anomaly was significant enough to be stated in a publication, that it goes into the database. And they are all different types, and sometimes kind of ambiguously described as an alarm, an oscillograph, capacitor, could be tripped, a problem with the generator, voltage, MVARs, so inefficient transmission of electricity, all of which were reported as being associated with the 1989 storm. All right, so we want to analyze data that we have. We have magnetic observatory data, we have magnetotelluric tensor data, and use those to estimate geoelectric fields, because it's that geophysical quantity, the geoelectric field, that's most interesting to the power grid industry. And the process that we're adopting here is actually quite straightforward, and I'm sure that the folks in this community really understand this in a very straightforward way. Just in an abstract sense, we have an input signal which is being convolved through a filter, and we get an output signal. In particular, these signals that we're interested in are generated, again, as already described, by solar activity that causes geomagnetic activity at the Earth, and that leads to the induction of electric fields in the heterogeneous electrically conducting solid Earth. And just show that schematically with that cross-section of Eastern United States. And again, that geoelectric field quantity is what's interesting to the power grid industry. Okay, all of that's qualitative, and I would say that we understand that in a qualitative sense, but we want to be quantitative. We want to understand not just that there were electric fields, but we want to know how big they were. We want to know where they were, when they were, over the course of the evolution of this magnetic storm. So we use real data, of course, magnetic observatory data shown there in the lower left-hand corner. That's the Fredericksburg Observatory. We marry that through convolution with magnetotelluric survey tensors, and there's a couple of guys deploying MT sensor systems, and that guy on the right is Paul Bedrosian, one of my co-authors. And with that marriage of these two important data sets, we're going to map out geoelectric hazards across the contiguous United States. All right, so again, another point that I think is well understood by this community, the electrical conductivity structure of the solid Earth affects magnetic induction and generation of electric fields. And so schematically, we have an electric current in space. It's time dependent, so it generates a time dependent magnetic field that by Faraday's law induces electric fields in the electrically conducting solid earth. The efficiency, though, with which that generation occurs and the currents that it drives depends on the conductivity itself. So currents flow very easily, of course, in high conductivity rock material. They have a harder time flowing in resistive material. And if you happen to have a power grid deployed across an electrically resistive rock structure, the current won't so easily flow through the earth, but could take the path of least resistance, which might be right through the power grid system itself. And this really is the source of the problem. These are uncontrolled, quasi-direct, they're changing, but on time scale slow compared to the alternating current that the power grid system is designed for, and causes problems. The alternating current, the power grid is supposed to be alternating about a zero baseline, and the system is grounded because they seek stability for the system. But during a magnetic storm, that stability is disrupted, and we have these quasi-direct currents flowing through the system. It causes, in particular, malfunctions, if you like, of transformer systems and distorts the alternating current waveform, and that leads to all kinds of problems. It can trip relays, it can damage transformers. In that picture, remember I showed you a damaged transformer, cause problems with the operation of a power grid. All right, so we're going to be using Magnetotolurk tensors. This is a map showing the amplitude of impedance derived from Magnetotolurk surveys across North America. I'm going to concentrate on the CONUS part of this map, but yes, we have Magnetotolurk tensors, of course, in Canada as well, maybe not as many as we want, where we want them for this kind of study. This map shows the amplitude and polarization at 120 seconds. If the ellipse is large, the impedance is high. If the ellipse is red, the impedance is high. If the ellipse is small and blue, the impedance is low. And we can see that we have a very heterogeneous impedance across North America, that due to the subsurface electrical conductivity structure of North America, which is quite complicated and very interesting. I want to emphasize a couple of things. One is that the impedance amplitude, which is shown there at the scale at the bottom, excuse me, has a big range, in this case, about 3 orders of magnitude. And that's important to realize because when it comes to, again, the efficiency with which these electric fields are generated in the earth, it really depends on this impedance, which is a huge factor when you can change the amplitude by a factor of 3 orders of magnitude, and when you can also affect the polarization and, of course, also the phase of the induced geoelectric field. See that the impedance is high in Ontario and in that little corner of Quebec. We also see that it's high in the northern Midwest of the United States and Minnesota. And I just want to emphasize, it's also high in the eastern United States along the Piedmont Formation of the eastern United States. It's a little bit hard to see in this map because a lot of those impedances in the eastern United States are highly polarized. They're very narrow needle-shaped ellipses. The impedance is high, but it's also very polarized there, and that's important to realize. So, and I would say it's also important to realize that the impedance is low in lots of other places, like in Michigan here and in much of the western United States. So just keep that in mind. We'll come back to this issue of the amplitude of tensors in the later part of this talk. So we're also going to be marrying those data with magnetic observatory data. We use the observatory data that were in operation during the March 1989 storm. Those were 1-minute resolution digital data. And we're using data from all of these stations, data collected by the USGS and by NRCan in Canada. And, we'd like to have more observatories, to be honest, but this is what we had in operation March 1989. And again, we're going to do what we can with what we have and just see where it takes us. So just concentrate for a second on these 4 stations, 2 in Canada and 2 in the United States. And I just circle them there to highlight that they're kind of along a line of longitude, similar latitudes. And this is what the data look like from those 4 stations for March 1989. You see at the top here, these 2 Canadian stations are doing quite well. Ottawa is very important to us because it's close to the United States. We're going to especially rely on those data for modeling, and show here the Fredericksburg data for the March 1989 storm and the San Juan data for the March 1989 storm. And even though it's not my fault, I want to apologize for the quality of the data from those 2 stations. Can't do anything about it. March 1989, I was still a graduate student. I don't know exactly what was going on at the USGS and why those data were defective. We see in particular the Fredericksburg data at an unfortunate period of time during the main phase development of the storm. The data actually are clipped at the top. And we just remain mindful of that. We can't do anything about it, but we remain mindful of that. We're going to be interested in this ramping up of magnetic activity here. Turns out, fortunately, not so interested in that particular period. And then we're going to be interested in this period right here, which is a very intense time of geomagnetic activity across the United States. This is San Juan, and also it had some significant problems, a huge data gap, right when we wanted to collect the data. Again, can't do anything about that, but we're going again to use these data, see what we can do to compare them with the anomaly data set that I was discussing. Just for reference, I have highlighted here the sudden commencements. These amount to the arrival of those coronal mass ejections that were illustrated in the movie. During a sudden commencement, the shock wave of the CME is arriving at the Earth and compressing the magnetic field of the Earth. The magnetopause, there's a current system that develops across the face of the magnetopause, and that causes pretty much a worldwide amplification of the local magnetic field that's measured at various observatories. And you can see that there in those examples. Afterwards, you have the development of the main phase, and it's then that the auroral oval moves down to low latitudes and causes problems with the CONUS power grid systems. Again, just emphasizing here, we're using this data to analyze electric fields across the United States. All right, just show some of the results here very quickly. On the left here, we show maps of the peak estimated 1-minute induced geoelectric field per hour. So each hour we look at the electric field that we're estimating, which has 1-minute resolution, and we plot the amplitude of the peak amplitude realized over the course of each hour. So there's 9 hours of time here, and these 9 hours of time are actually centered on the sudden commencement that was responsible actually for causing the Quebec power outage. This is not the period of time that's most interesting for CONUS, but I just want to illustrate what's going on in CONUS during this period of time. It's during this hour 7 to hour 8 of March 13, when we had the blackout in Quebec, and showing here the amplitude of our estimated electric fields. As we might expect, because the impedance is high in the northern Midwest of the United States, and the impedance is high along the Piedmont of the Eastern United States, we have high electric fields in those places, okay? So with magnetotelluric data, we can estimate the amplitude there. With understanding of geology, we can understand why the amplitudes are high there, and actually also, importantly, why they're low in other places. And the scale that we're showing here for the peak geoelectric field has a big range, over 2 orders of magnitude, actually, from 0.2 to 20 volts per kilometer. That might seem like a rather modest electric field, 20 volts per kilometer. Well, when you integrate 20 volts per kilometer over a power grid line that might be 100 kilometers long, that's quite common. You end up with 2,000 volts of DC current, and that really is the base of the problem. On the right here, we're showing correspondingly the anomalies that were experienced across the contiguous United States during this 9-hour period of time. And I just want to concentrate on this one period of time here, hour 11 to hour 12 of March 13, and see what we can say about that in terms of the induced electric fields and the inducing magnetic field. All right, so for that particular hour, again, on the right here, showing the geoelectric field amplitude over that particular hour, and the anomalies that were experienced across CONUS during that particular hour. We can look back at our modeling and see what was going on in the ionosphere. And during this period of time, we're showing here in the upper left-hand corner, the Electrojet system of the auroral current system over North America. This is derived from magnetic field data collected at the various observatories. And we see that it's essentially a westward directed Electrojet generating on the bottom here, southward magnetic field. So this is the development of the main phase, start of the development of the main phase of the magnetic storm when the magnetic field actually decreases in intensity. And we see that going on here with the generation of these magnetic fields across CONUS United States. That's an early phase of the storm. All right. So now I want to concentrate on the main phase, really the depth of the storm when the auroral oval really opened up, moved south, and really started to interfere with the power grid systems across the United States. Again, 9 hours of time here, going from hour 18 of March 13 to hour 2 of March 14. Okay, so 1 hour, next hour, etc., progressing through time. Importantly, we see at this period of time from hour 18 to about hour 21, things are fairly calm. The geoelectric field has low amplitude across the United States, and correspondingly, there are few power grid anomalies across the United States. But as the geoelectric field starts to amplify, and we see that here on the left, we see correspondingly, there are the development of these the realization of power grid anomalies across the contiguous United States. So we're seeing something very important here. Using the Magnetotolurk data, marrying it with the magnetic observatory data that we understand have their problems, still we can use those data and do a pretty good job of estimating where and when geoelectric fields are experienced across the contiguous United States, and where and when power grid anomalies were experienced. There's quite good correlation here, and I'll just demonstrate that by looking a little bit more closely at a particular moment in time. This is a period of time here, hour 21 to 22 of March 13, when the magnetic storm was still amplifying. The auroral oval was still developing across the United States. Again, on the right here, showing those peak geoelectric field amplitudes across CONUS and the realization of the anomalies across CONUS. We can look back at the model of the geomagnetic field and infer the structure of the Electrojet system. Interestingly, here we see on the top left that the Electrojet is actually an eastward Electrojet. That's the opposite of what we showed in the previous kind of 1 hour period of time that we zoomed in on. So that was a westward Electrojet. So here we have an eastward Electrojet generating magnetic field variations, not showing up here as particularly large in amplitude, but of course it's the variation that's important that induces the electric field and causes the anomalies. Okay, so we have two different kinds of current systems which are turning out to be hazardous for CONUS, westward and eastward Electrojets at different local times. So, all right, going back to that 9 hour period of time that I was showing before, and now I'm going to zoom in on this period of time. This is the most intense part of the magnetic storm. This is when DST reached its greatest depth. And it's at this period of time that most of the anomalies were experienced across the United States. See that here in the map on the right. And we see on the left, the amplitude of the geoelectric fields. The geoelectric fields are actually a little bit less intense in the northern Midwest and most intense in the eastern United States. And there we have it. We have this very nice correlation between the natural phenomena and the effect on the power grid system. Looking at that in a little bit more detail, again, geoelectric field on the top right, anomalies on the lower right. Looking now again at the Electrojet that was, we can understand was generated across the contiguous United States. It's directed to the northwest, and the magnetic fields that it's generating tending to be directed to the southwest, just as per Ampere's law. And correspondingly, we see that correlation with geoelectric fields and the anomalies. All right, so we can take these results and we can integrate them over time and understand essentially what the hazard is. This is, you know, insofar as hazard is kind of a summation of lots of different time varying effects. We can look at the maximum geoelectric field that was realized over the course of the storm for March 1989. And there you have it on the left-hand side, ranging in amplitude quite considerably across more than 2 orders of magnitude, really almost 3 orders of magnitude. Because we show it saturates on the lower scale. And see where those geoelectric fields were realized, and then look at the anomalies. This is all the anomalies for the contiguous United States, and this is an important plot that I like to show to my leaders. Look at where the anomalies are, just think about them for a second. They are being experienced for many of the largest cities of the United States, the megalopolis that extends from Washington, DC, through Philadelphia, New York City, up through Boston. You know, if we want to look at where the hazard is for this particular phenomena, that's where we should be concentrating our attention. And again, thanks to the Magnetotelluric survey, the survey that was supported by the NSF and managed out of Oregon State University, and which is now being funded by the USGS to complete the survey across the southern United States, again, in collaboration with Oregon State University. With those data, very powerful data, and they really are giving us important insight to this important space weather hazard that's realized at the surface of the Earth. All right, so I just want to emphasize that the impedance is performing a very important role in organizing the geoelectric hazard, and we can analyze that and inspect that with a little bit of detail right here. So remember that map I showed of the impedance ellipses? So we take the maximum amplitude off of those ellipses for the amplitude in the most polarizing direction at 120 seconds, which is the Nyquist period for the 1-minute observatory data that we have. We plot that transfer amplitude on the horizontal axis here, and then look at the maximum geoelectric field that was realized over the course of the magnetic storm for each one of those tensors. And we plot that amplitude versus the geoelectric amplitude versus the transfer amplitude on this log-log plot. And we see really that the geoelectric, or sorry, the impedance of the solid Earth is the organizing influence for the geoelectric hazards across the contiguous United States. That's true across orders of magnitude. That's important to realize because the space weather community tends to be focused on the current systems themselves without necessarily appreciating that the solid Earth is playing a huge role here in organizing the geoelectric hazards, essentially putting them where they are and affecting their amplitudes. We see that, and I just fitted a nice power law there to emphasize that effect. So across orders of magnitude, that organization is occurring thanks to impedance. Now, what about the space weather currents? Well, same plot here, except that now I'm dividing the data set into 2 parts. One is the part that is of lowish geomagnetic latitude, less than 50 degrees north, and another part that's higher than 50 degrees north geomagnetic latitude. And there we have it. We have this very nice kind of dichotomy of data, and it shows the effect of the overhead current systems on the organization of the geoelectric hazards. It's not as strong of an effect as impedance, but it is certainly detectable. I think this plot demonstrates that those two effects are important. The space weather effect is important for giving the overall amplitude of the magnetic storm. But the geographic organization is primarily due to impedance and secondarily due to the organization in geomagnetic latitude due to the electrojets. All right, so just want to compare these results with other kind of more panoramic results that we've been developing at the USGS and now at the USGS in collaboration with the University of Colorado. This is work that was spearheaded by one of our postdocs at the time, Greg Lucas, who now works at the University of Colorado, and basically going through the process that I was describing for the March 1989 storm, but doing that for multiple storms and then doing some statistical analyses of the results to understand what the geoelectric field is across CONUS and then projecting that on to the power grid system itself. And that is this map here, which we describe as a geoelectric hazard map, again, showing where they're high and where they're low. And just as for the 1989 storm, if you look at decades worth of magnetic storms and do this statistical analysis, you see that the storms tend to induce high voltages on power grid lines in the northern Midwest and in the eastern United States across the Piedmont Formation. Again, the amplitude of these voltages differs quite significantly from one location to another by more than 2 orders of magnitude. And that means that the currents that you could expect to be induced in the high hazard places can be typically about 2 orders of magnitude higher than they would in the low hazard areas. So that is an important and large amplitude effect that can be usefully applied to projects which are intended to mitigate power grid hazards experienced during magnetic storms. I'm very proud of this result, not because I was the lead investigator, that was Greg, but just being associated with this. And I will say that I'm also proud of the attention that this product has received. We received press from IEEE Spectrum, Energy Wire, Physics World, National Geographic, Scientific American, Bloomberg, and spaceweather.com. So again, I'm proud of what our group has been able to do in this respect. There's an ongoing project which we're collaborating with NOAA to translate these results into real-time maps. Again, using the Magnetotelluric impedance tensors, marrying it with magnetic observatory data, but doing that all in real time in order to map out the geoelectric field as it's experienced across CONUS during magnetic storms as a service to the power grid industry. All right, so move on to my conclusions. Mapping geoelectric magnetic fields across CONUS during the 1989 storm presents hazard or problems or challenges due to the sparsity of observatories, the quality of the data, and the incompleteness of the survey across the Southwest United States. We know we have some problems there, but in terms of, for this particular storm, but in terms of looking at the anomalies for this particular storm, we still do a pretty good job of estimating the electric fields and understanding where the electric fields are high and where they're low, and seeing the correlations of those maps with the anomaly maps. We can see very clearly that power grid interference was concentrated where surface impedance is high and where and when geoelectric amplitudes were high. Grid systems can be affected by a number of different current systems in space. I was showing examples of westward and eastward electrojets, and by over a variety of local times. So there is not a single current system, at least during a storm as intense as March 1989, that we can point to as being particularly hazardous. It depends where you are, when you are, and the fact that we have so much magnetic activity during this intense magnetic storm means that there's abundance of current systems that contribute to the hazards. Geoelectric hazards across CONUS are primarily organized by surface impedance. I think the MT community can be kind of impressed by that. But due to auroral electrojets, a weaker organization is also seen with geomagnetic latitudes. This work demonstrates the need for a denser network of geomagnetic monitoring, I would say particularly across the Northeast United States. The need for completing the MT for a complete magnetotelluric survey across Canada. I think that would be terrifically impactful and important, especially across Quebec and Ontario. And the importance of completing the national MT survey across the contiguous United States. There's a whole lot of work that remains to be done to integrate these studies, to understand power grid vulnerability in the United States. Certain parameters are actually not well known and are causing difficulties in analyzing the GICs that are actually realized on power grid systems. We don't know, for example, the grounding resistances at most of the substations across the United States. That needs to be addressed in order to use Kirchhoff's law to properly estimate the GICs that would be induced on the power grid system during a storm. Right now, we're just estimating the electric fields and the voltages on the power grid line systems. And it's possible to take those kinds of geophysical and engineering analyses and put them together into a more formal analysis of risk. And that also is work that remains to be done. So thank you very much. I appreciate the opportunity to address this community. The Magnetotolurk data are indispensable. And I just want to say I am on a kind of a mission to evangelize the importance of these data for multiple applications. I appreciate that the data are collected for understanding the solid Earth and the structure of the solid Earth, but they also have some other important utility. And I just think that's great. Thank you very much.
Well, thank you very much, Jeffrey, on behalf of all the listeners of today and all the listeners of the future who are going to watch this recording. I'd like to thank you for a wonderful presentation. I open it up for questions, and if there isn't a question now, so I'll jump in and ask a question, and that's with regard to the comment you're making around how it's primarily organized by surface impedance. Is that implying that, in fact, contact charges on conductivity boundaries is a stronger effect than induction, as in the whole of the deep pile? At long periods, you're going to have quite deep induction, right? So I'm just particularly, I was looking at one of your brightest effects, which was up in Wisconsin and North Dakota. And I was wondering whether that comes about because of the juxtaposition of the Williston Basin sediments, the conducting sediments, and the Canadian Shield in Wisconsin.
Yeah, Alan, the short answer is I don't know. The long answer is that for this kind of study, we're just using the impedances as empirical impedances. Yeah. They will have lots of different reasons for being what they are. And of course, there's complicated frequency dependence. So it depends on which frequency you're looking at to understand which kind of depth you're probing. But you're asking quite detailed questions, and I don't know the answer to that particular question about this certain formation you mentioned in Wisconsin. The analysis here is just purely empirical. The impedance, what it is, due to combination of charges accumulating on discontinuities and also straight induction. Could be coast effect in some places.
Right.
We're not discriminating. We're just using the impedance tensors as they are. You know, I will say that my colleagues like Paul Bedrosian and Ben Murphy, probably better at answering questions like that. And it's important for understanding why the hazards are high where they are and why they're low where they are. And so that question you're answering gets at that, but it's not something I've been focusing on.
Okay, I see Darcy's got a hand up. So you're available to speak now, Darcy?
Hi, can you hear me there?
Yeah.
Yeah.
Okay, great. Yeah, hi, Jeff. Thanks for the great talk.
Darcy, thank you for joining and congratulations on your recent space weather paper.
Oh yeah, thanks. Thanks for that. Yeah, I was going to just comment on that as well because I'm assuming these are long period data. So
They are.
highest frequency you have is probably 1 second or.
Well, the highest frequency of the MT data is about 10 seconds ish, but we're really limited by the 1 minute resolution of the magnetometer data. So really, we're talking 120 seconds.
So when you're plotting the surface impedance, that plot of the cross plots, you're using the highest frequency data that you have to make that plot. Is that correct?
Yeah. So I concentrate. I can zoom back here. I think. Let me see. I still have control. So that impedance map that I showed. Give me oh. Got to slow down. There we are. That is at 120 seconds, and we've looked at this at other periods, 10 seconds, 1,000 seconds. You know, qualitatively, the impedances are still high where they are high at 120 seconds and low where they are low. Of course, the amplitude's different, but just for qualitative purposes, qualitative discussion focusing here on 120 seconds because, again, we're limited by the 1 minute data that were available during the 1989 storm. That's really the focus.
Okay. Okay, that makes sense. Then I was also just another question. What's the pulse of the American power industry on this work? Is there significant buy-in from the power industry, and are you collaborating closely with kind of power industry partners?
I'll say it's complicated, partly because there's a lot of different companies. So understanding, summarizing their reaction, I don't know would know how to do that. There's of course a lot of personalities involved, but I will say that speaking in the most general terms, the industry takes GMD seriously. The NERC, North American Electric Reliability Corporation, which includes Canada, has commissioned studies, and I can say when I've gone to some of their meetings, there are people who are conversant on the subject of magnetic storms. Having said that, they are primarily engineers, and they have their own, domain of expertise, and their awareness of geophysics is not as strong as it is in engineering. Of course, I can't say that me as a geophysicist, I know that much about engineering, really. So we all have our kind of niche and our roles. And I think that there's good opportunity for more communication between the geophysicists, be they space physicists or solid earth geophysicists, to explain and to communicate the issues that are important for the power grid industry, and really importantly, to put the geophysical results into terms that they can understand and use. And there's lots of opportunity there for work. That's where it's happening.
Yeah.
We're trying to do some of that, but if other people want to participate, Darcy, you're included, I would say you'd be welcome.
Okay. Yeah, thanks so much. Thanks for the talk again too.
Yeah. My pleasure.
Thank you, Darcy, for the question. Just we have one from Abbas Fani, and thank you, Abbas, for your question. I'll read this out, Jeffrey, so it gets in the recorded version. Thank you so much. What's your opinion about stopping 220 volt power lines and replacing them with 12 volt or 24 volt, or generally green electrical energy as a future to be safe from magnetic and solar windstorms?
So I don't have an opinion about that that's very strong. I might be I'm not sure what this question is. Maybe it's about people wanting to go off the grid, have their own generators. Let me just be frank. I don't have my own generator at home. I use regular electricity, and you know, I can't say as a government employee that people should go out and buy generators. I just wouldn't be a responsible person to do that. I am trying to promote a subject which is important for the population of the United States. The grid systems that we have today and the reliance that we have on electricity as it is today. And I don't think that, I mean, if a few people want to go off the grid, fine. But at the same time, I'm going to concentrate my work where the impact is most greatest. And that's for the majority of the population, the majority of the industry that relies on the electric power grid that we have. So is that an answer? I don't know. Is that an answer?
It's a perfect answer, I think, Jeffrey, in as much as we have the grid systems we have and they've been developed for historical reasons. And I guess Abbas is looking to the future when possibly we'll have much more local generation. For example, I have solar panels on my roof.
Yep.
And if every house had solar panels on its roof, then we wouldn't need as much interconnectivity in networks. They'd only be for industrial supply. Then.
That's right. Industry is not a trivial issue. So I think there's always going to be a power grid supplying us with kind of the base power supplies that we need. I think that this kind of work does inform future projects for so-called smart grids. We want to be smart about our smart grids and understand the hazards that they would experience, especially if the power grid lines end up being really long. If you have really long power grid lines, then these faint voltages really become, or faint electric fields really become an issue when you integrate them across the length of these long power grid lines. So,
Joanna Alves Ribeiro has a question, and I know that having access to the topology of the power network is not always easy, but are the power transporter companies open to the installation GIC measurements devices like Hall sensors?
Yeah, so a couple questions there. One is that the topology of the power grid in the United States is actually, I'm going to try to forward here, is public knowledge. You can get that from the Department of Homeland Security. You can also get the locations of most of the power grid. There we are. Most of the power grid substations. A certain amount of work, kind of using that and integrating it. So that information is around, and we use it, like for this hazard map. But with respect to the GICs, so this hazard map is just voltages, right? It's still a geophysical signal projected onto the power grid system. The actual response of the power grid system, which is the current that would be driven by these voltages, again, depends on Kirchhoff's law. You would need to know the grounding resistances, the resistances of the lines, and their interconnectivity in order to properly calculate GICs. Calculating them is one thing, and of course you want to compare that with measurements, and whether or not the power grid industry is open to it. In the United States, the Federal Energy Regulatory Commission is now mandating it, and those data are being collected and will be publicly available. They will be of some use. We can do kind of correlation analyses of the GICs and understand how those are related to magnetic storms. But again, until we know the grounding resistances, we won't be able to do the forward calculation with much accuracy. So.
Thank you, Joanna. I've got one more question, Jeffrey, and that's with regard to the transfer function. If you want to just put up your image again, showing the magnetic field in, the transfer function and the electric field.
Ah, yes, my flow chart.
The flow chart. Yeah.
I use that a lot. Sorry, I'm not quite in the right mode here. But
that one, yeah. That one, yeah.
Sorry, there it is. There we are.
Now, the point is what everything you've shown us has been, if you like, first order. In as much as you've taken the transfer functions derived by US array and input your time series and got your estimated electric fields out. But the transfer function itself was derived assuming uniform plane wave field, and yet your interest, of course, is in highly non-uniform plane waves, and that transfer function will change.
Yeah.
As the sources change. And in fact, if you're under a highly non-uniform source field, you'll get much less electric field than the uniform case. But if you're in the far field of a highly non-uniform field, you'll get more electric field. Not a lot more, maybe a factor of 10%, but certainly in Canada, the estimates we've been getting from these sort of measurements, or these sort of modeling techniques, have been, I would say, overestimates of the electric field, because we're predominantly beneath the electric, the source field itself. And so our convolution filter will generate less electric field.
Alan, that's a great question. And I'm going to be the first person to say, I wish we had more accuracy in everything that we're doing. And this discussion of plane wave oftentimes comes up, especially when, talking to the MT community, because they're curious about it.
We worry about it.
Yeah, they're worried about it. And, I'll say, the signals that the MT community is interested in are oftentimes very subtle, because they're interested in, this difficult inverse problem for inferring subsurface conductivity structure. You mentioned 10%. I'll tell you, I would be thrilled if we only had a 10% error. I'm thinking that the errors, like in this hazard map shown in the lower right-hand corner, it's about a factor of 2.
Okay.
That's a big error, okay? In some respects, but in other respects, it's actually not that big, because just pull back and realize that the range and amplitude of that map is orders of magnitude.
Right.
And so we think we have a factor of 2 error, not so much introduced by the plane wave approximation, but by the sparsity of magnetic observatories. Right. We think that's really the primary source of the error. If we had lots and lots of stations closely spaced and we're monitoring continuously, we could do an interesting study of the plane wave approximation. That is not on the horizon. And it would be interesting and useful, but I will say that you're getting at kind of smaller parts of the error, which right now are related to the sparsity of observatories, and a factor of 2. I think a factor of 2 would probably be an enormous error if you're just doing MT analysis and then doing an inversion. But for this kind of work, you can tolerate some pretty big errors, actually, just because of the range of amplitude, which is huge.
Okay, the final question. I guess no one else is asking. So it's the Carrington event was, forgive me, 1864?
1859.
59. I'm trying to remember when Gauss that was about exactly the year that Gauss started installing his observatories, right? The Toronto Observatory, I think, dates from
yeah, that's a good question. God, I'm trying to remember the magnetischer Verein. I think that was in the 1840s. And it was different than the kind of, what we normally think of as magnetic observatory operation. Gauss got people together around the world to make magnetic measurements at fixed stations. There were only fixed duration campaigns of a few days. In those days, they didn't really have that much coordination. And so basically the invitation is, on the following days, please make magnetic field measurements visually.
Yes.
And so that was done around the world. It showed an important issue, that magnetic activity is global, but it wasn't a detailed analysis of magnetic storms, and it really didn't contribute. It didn't contribute at all to.
But it'd be interesting to try to see what the effect of the Carrington-like event would be like.
Yep.
In North America, given our infrastructure we have.
Yeah, and we want to do that. And one of the reasons I'm interested in kind of characterizing the organization of the magnetic storm hazards. Here, I think I can get out of this and zoom down. Like I'm doing here, is to try to find a way to at least generally parameterize magnetic activity, across geography for a particular storm. Do that for other storms. Maybe we can understand that there's some patterns involved. Right. I think that this power law relationship would probably be a little bit different from one storm to another, for example. Yeah. The organization by latitude might be a little bit different from one storm to another. But if we can come up with some generalities, then we might be able to project forward to bigger storms like 1921, like 1859, to better understand. Again, the MT data are making a huge contribution to that kind of study, but that's one of the things I'm anxious to look at. I don't know exactly where it would go, but as with other analyses we've done, we're going to do it empirically. We're going to use real data to really analyze this. So,
brilliant. Well, I'd like to, on behalf of everybody who's listening today and future listeners, I'd like to thank you again very much, Jeffrey.
Alan, my pleasure.
Enthralling talk.
Yeah, and I hope I could give another presentation in the next year maybe. That would be great. So.
Yeah, if we have a big storm between now and then, you'll have a lot to say. We had a roar actually the last couple of nights here up here.
That's right. Yeah, but you're up in Canada, so. Anyway, thank you everybody, and I really enjoyed this. So
thank you. Okay, I'll just sign off by reminding everybody of next week's EMinar, and it's me talking at the same time. I'm giving a history of the discovery and understanding of the North American Central Plains conductivity anomaly at the same time. So see everybody in a week, and thanks again, Jeffrey, and thanks everyone for attending. Right, this recording will be online in a couple of hours. And Jeffrey, if you could send me your, always gone. Right, bye everybody.